Thank you very much for the introduction, and I really appreciate being invited here to speak. I spent 11 years at the University of Iowa, and people would say, oh, you're from Iowa State, and it's kind of nice to actually visit where everybody thinks I'm from. So this is really fun. What I'll be talking about today is HCI in the car, or in the automobile, and some of the challenges that come with that. And I imagine that all but maybe a few of you are actually have any interest in HCI in the car, but I'll probably be hopefully connecting with you in the sense of showing some of the challenges that face HCI in general as we move into the world. So HCI in the world might have been a better title for this. And when you take HCI or computers and put them in the world in the context of more complicated interactions with people that have consequences, bad things can happen, and also some very good things can happen. And so that's what I'll be talking about. So before I get into the details, I'd like to acknowledge a number of the students who actually do all the research that I'm talking about. I just get up and talk about it. They actually do the work. Shannon Roberts on the left, June Boom Lee, Tony McDonald, and Aaron Chiu. I'll be talking about some of their contributions as we go through the presentation here. A couple of them are graduating, so if you're needing an amazing PhD in industrial engineering specializing in human-computer interaction stuff, let me know. So HCI in the world, I'll be breaking this talk into three sections, looking at distraction and interruption. Obviously in the car, texting teens is in the news, distraction in the car is a big deal. But interruption in other situations is also a really big deal. If you look at medicine, 90,000 people a year die because physicians and nurses make mistakes. Oftentimes those mistakes are preceded by interruptions or distraction. Distractions are a big problem. State detection and feedback, it's getting increasingly possible to instrument everything and everybody. Can you use that instrumentation to estimate the state of people, provide them feedback, and guide them to better, healthier behavior? In the car, you can certainly do that. I think in the world in general, that's becoming increasingly possible. And then the last topic there, managing autonomy. As computers go out in the world, they're getting smarter and they're controlling more stuff. And are we ready for them to manage our lives and control our lives to an increasing degree? And we're seeing that in cars. You may have seen the Google car. It's getting really pretty amazing. The other manufacturers are doing the same thing. There's projections in 10 years there'll be a fully autonomous vehicle on the road that you can buy. And those are projections by reputable people, not myself. So the basic message here is looking at computers in context, in the complicated context of the world, and where there are consequences for mistakes. And I'll go through a couple of those examples. So distraction and interruption in the car, this is becoming an increasing problem as it becomes possible to stream more and more information into the car. This is the back cover of a Wired magazine where they have this future view of the world in 5, 10, 20 years. A head-up display that's going to be feeding you all sorts of useful information and useless information. I think the car of the future will almost certainly include Starbucks coupons that flash up and tell you when you need to get your coffee next. But also probably quite feasible, giving you some information about the state of the driver ahead there, that little red warning that the person's a DUI offender and you should stand back. And this sort of information is on the verge of becoming reality with the idea of the connected car. And so the data streams are going to be there. There's large format head-up displays. So this is not that far off. Putting information in the world in front of people can be a good thing, may keep you safer, but there's also a downside. Our attentional abilities are severely limited. We can't do two things at once. And that's, I think, nicely illustrated by this. This is a product. It's information that's presented to skiers and snowboarders, a head-up display on goggles, very nicely formatted, gives you information about your speed, 54 kilometers an hour, your altitude at each meter as you descend the slope, even gives you your battery and the time and the seconds into your run, for example. And this is the goggles themselves, which are on the market. If you have the money, you can buy these. Interestingly, on the box for these ski goggles, it says, "Not for use while skiing." So you can see the lawyers had a voice in the vote here. At least they got the label on the package. But this is the sort of thing that is, I think, coming for cars as well. And the manufacturers don't want the liability, but at the same time, there's the potential for revenue that's really substantial. So there's this idea of the explosion of apps that we've seen on smartphones. The same sort of explosion is happening in cars. So you have these little pop-up displays. You have, in some cars, even a 19-inch LCD panel, huge panel, with all manner of apps and directly sync to your smartphone in some cases. I was at the SAE conference last week in Detroit, wandering around the exhibit hall, and Hyundai was displaying one of their head units similar to this, and you can click Explorer and get a full browser that you can surf the internet. A full QWERTY keyboard pops up on the touchscreen that you can type queries as you drive. Just crazy. And we asked the engineer there, so can you do this while you drive? And they said, sure, but of course it would be the passenger using it. So they have a lot of faith that the driver will be responsible. I'm a little skeptical about this. So this is a nice illustration of the general problem that confronts drivers. Try reading these two sentences at the same time, and you quickly find your mind can't do it. It's extremely difficult to split your attention between two things and do two things at once. You do one or the other, or your performance on one degrades your performance on the other. I think something that at some level is intuitive, but at the same time, I think a lot of us view ourselves as being good multitaskers. And the irony is, the better you think you are, the more practiced multitasker you are, the worse you are at focusing your attention when it needs to be focused. And I found this myself. I was driving back from Iowa City. I'm collaborating with the folks there on the National Advanced Driving Simulator. Was there for a week. Coming back to Madison, I was listening to the stereo in my car, which I thought was just like a radio. You put in a CD, though, and it reads that CD onto a big terabyte hard disk. So it's really like a computer that is behind the dash, not just a radio. And my wife had been driving, and she had been feeding in Adele CDs, and I was looking for Springsteen. And so I was coming back into Iowa City, and I thought, okay, I want to get Springsteen, get rid of this Adele. And so I was looking down at the screen and back and forth, trying to scroll through and find Springsteen. I looked Springsteen, and then I looked back to the road. And I discovered that I hadn't looked back to the road in a while. And I didn't hit anything, nothing untoward happened. I just had this sinking feeling that I could have died looking for Springsteen. I guess there's worse ways to die, but it was disturbing. And it was particularly disturbing because that same month, this paper came out called Scrolling and Driving, How an MP3 Player and Aftermarket Controller Affects Driving Performance and Visual Behavior. And I helped write this paper. So you'd think I would know not to scroll through songs as I'm driving, but I thought this was just a radio. So the point here is that this seemingly innocuous technology, the car radio, is extremely distracting. And I'm the sort of annoying person that tells you and nags you not to talk on your cell phone while you drive, not to text while you drive. I've never talked on my cell phone while I drive. I study distraction. I'm a safe driver. Well, I'm not a safe driver, but I don't do anything distracting when I drive, or so I thought, and it just sucked me in. And so here's some data from a study we did on scrolling and driving. And the point of this study was to understand whether an aftermarket controller that was designed to make a MP3 player, an iPod, more consistent with driving, make it easier and safer to use while driving. So you have this nifty little joystick type thing that you can scroll through your songs. And what we found in the simulator is something quite interesting. These 4 graphs are broken down between construction and traffic. Those are just 2 situations that we wanted to put people in the car, on the road. Sort of demanding situations where they were encouraged, they sort of had to keep looking at the road. So you couldn't just ignore the roadway. And what these are is density curves showing the distribution of glances, the duration of the glances. So along the bottom there, you see the glance duration in seconds, 1, 2, 3, 4, 5, 6 seconds. My little Adele Springsteen moment, I was out here. This is really bad. Chance of death goes up dramatically with glance length. And what you see, the 2 vertical lines there are the 95th percentile. These are the tails of the distribution. The tails of the distribution are important because that's where bad stuff happens. And the black bar is in the first 15 seconds, the gray bar in the last 15 seconds of these searches. So these are sort of searches through a long list of songs to find a song. Sort of like what I was doing. So on the top is the MP3 player. This is an iPod. On the bottom is the aftermarket controller that's supposed to make it easier. And what you see is that last 15-second distribution, it gets shifted to the right with the aftermarket controller. You can see the gray bar is substantially shifted to the right in both cases with the aftermarket controller. That's not what you hope when you've designed something to be used while driving. They actually made it worse. And it just goes to show how difficult it is to design a product well for the driving environment. You can screw up and kill people, which is not the case with Windows 8. You can annoy a lot of people with Windows 8, but unless they're using the tablet when they drive, you're unlikely to actually do people in. Whereas when you're designing this stuff for the car, quite possible. So what I'll talk about now is a little bit more on this issue of designing to avoid distraction. And one of the challenges in any design environment is doing user evaluations in a way that's consistent with the product cycle time. So getting an evaluation done quickly and a design change and doing that iterative process, you can't spend 2 weeks for each tweak of the interface. So what we've been working on is a computational model of the driver to understand what leads to these long glances. And to do that, we've been building on the ACT-R framework, which many of you are familiar with, long-standing, 30 years in development model of human behavior. Unfortunately, this model of human behavior is sort of like a disembodied brain that doesn't have any eyes. Information just magically flows in. It doesn't also switch between activities, critical for driving. So Junboom Lee, the graduate student I pointed out earlier, he's developed this ACT-R with eyes in collaboration with Dario Salvucci and Drexel. What we're doing here is taking the salience map idea from Itti and Cook and merging it with the distract-R or the ACT-R framework. So what ACT-R does is it describes the tasks the driver is doing, gives you some top-down influence on attention, where drivers are expecting things based on the goals and the tasks they're doing, and then the salience map identifies where the driver is likely to, where the driver's attention is likely to be drawn based on the features of the interface. So things like color intensity, orientation, that in the environment combines to guide what you're going to look at. Both of those combine to create this activation field, which is basically a prediction of where the eyes are likely to go on the display. This gives you a little bit more detail from Itti and Cook, their work showing this picture in the upper left, filtered through orientation, intensity, and color, combining those to identify the salience of different areas in the display. So you can see the little money bag there is highlighted in bright. So it's a heat map of the likely location of a glance. So we want to be able to take this sort of computational framework and predict where people are going to look on a display. And if you've created a display in the car that has salient elements that are not corresponding to where the driver needs to look to get information, what will happen is the driver's eyes will be drawn to those salient elements, and the driver will not find the information they need and will have to glance at another location and another location. Each of those glances adds something like 300 milliseconds to the time off the road, and those 300 milliseconds quickly add up and contribute to risk of a collision. This is a Ford Sync system view. You can see the radio station, AM, FM up in the upper left, presets on the right, this sort of tag cart thing in the middle there. And what we've done here is applied the saliency map to that to identify what is going to draw drivers' attention. So this is a function of the color, contrast, orientation, and how those things are influenced by their co-location. So that gives you a sense of what drivers are going to look at. So this would predict they're going to look at the little shopping cart icon. Maybe that's good, maybe it's not. Probably not the place where you want drivers looking, and to the AM, FM indicator. And not at all to the street name in the upper right, which may be appropriate. What we've done here, which is a little bit dark on the right, is we've identified some functional grouping. So we've highlighted the presets with a color background. And what you see by doing that, by adding that background, we've shifted the attention away from that little shopping cart. So very quickly you can try out these new designs and see what it might do to the display, driver's attention to the display. What we've done here is we've changed that Main Street label from a constant on label to a flickering label. On, off. And what that does is it just sucks drivers' attention right into that item. Really powerful, very salient cue that you can see that's the thing that they're going to look at, which, again, might be the right thing to do, might not be the right thing to do. The point of this is that you can run it through the computational model and get a sense for how that display is going to affect driver behavior in a minute rather than a week, as you might with eye tracking study across a 24-subject person population. So that's what we're doing to support design, hopefully reducing distraction, creating displays that attract the driver's attention to the thing that matters at the time that it matters. So the next thing I'm going to talk about is state detection and feedback. Cars are getting really smart. So the instrumentation that's moving into cars, the computerization that's moving into cars is really tremendous. Some people have described cars as having wheels to keep the computers from scraping across the ground. So we think about cars as modes of transportation, but increasingly they're sort of mobile computing platforms. And with that comes a tremendous amount of instrumentation. The upper right is a potential instrumentation for the seat to capture your body's posture, so you can get that sort of information. Lower left here is eye tracking, face tracking, increasingly feasible, and in some cars, even today, the Lexus has a head tracking system that can tell when you're looking away from the road versus looking towards the road. Key fobs that remember who you are and your preferences, and drive-by-wire systems that can measure in great detail how you're manipulating the steering wheel, accelerator, and brake. So cars are basically highly instrumented ways of monitoring behavior, which introduces some interesting possibilities. Tony McDonald has been doing some really interesting work looking at algorithms to detect various types of impairment. So part of these are to detect impairment associated with distraction. If the car knows that you're distracted, the car can respond and keep you safe. So that's useful. Similarly, if the car knows that you're tired and drifting off to sleep, the car can alert you. At the moment, that's kind of a mundane alert of a coffee cup popping up on the dash. That's what Volvo and others have done. If you have better ideas for alerting somebody, let me know. I'm working on that problem right now. But Tony's also applied this to using the car as a medical diagnostic tool. So we're doing a study with some folks at the University of Iowa in the neurology department, trying to understand whether the car can distinguish between people who have sleep apnea and are complying with their CPAP regime versus not, just from the instrumentation that we put into the car and their normal driving patterns. And it turns out Tony's been able to do that. So what he's been doing is combining algorithms like support vector machines, decision trees. They take these various variables and look at levels of those variables to predict whether you're tired or not, or you've been adhering to your CPAP regime or not, looking at Bayesian networks and neural networks, and then ultimately combining these different techniques with ensemble methods, which is basically just having each of the algorithms vote in terms of which state they think the driver is in, sleepy, awake, distracted versus not. And the particular ensemble method that I'll tell you a little bit more about combines decision trees, cleverly named random forest. So you have a bunch of trees and you get a forest. Random forest is a very powerful classification tool. And for many of you, this is going to be a review of maybe your introductory human factors course where you looked at the warning system characteristics, how good warnings are. In detecting driver's state, you can always detect when somebody's drowsy by saying they're drowsy all the time. So that's correct some of the time, but oftentimes not. So you have a very high false positive rate towards the right, but you get all of the cases. Or you can say they're never drowsy, and you never falsely say they're drowsy when they're not, but you miss a lot of cases. And so you'd be low on the true positive, but low on the false alarm or false positive rate. So random classification is therefore along that diagonal line. So that's an area under the curve of 0.5. Area under that diagonal is 0.5 of the 1. And then perfect classification is area under the curve of 1. So you always detect when they're drowsy, never give a false positive. Okay? So that's a good way of measuring performance because it trades off the tendency for false positives and false negatives. And in that framework, what we did, what Tony did really, is he looked at a random forest model based just on the steering wheel behavior. This is just looking at the steering behavior of drivers to detect whether or not they were drowsy. And compared that to Perils, which is a vision-based system. It's the percent eyes closed. So when you get drowsy, your eyes closed, you have long blinks, you have drooping eyelids, all that's diagnostic of drowsiness. And what we see here is that Tony's method using steering wheel movements outperforms this very expensive vision-based method using eye closure. So really promising because this is something that could go into your car almost today or tomorrow. This doesn't take extra information, doesn't take a expensive eye tracking system. So really interesting to see what can be pulled out of the signal that's coming off your car. And then this information can be used to coach you to a safer driving behavior. That's what we're hoping. So your car's getting smarter about you, about your behavior, about your state. The car can also get smarter about the state of the world. So cars in the future hopefully will take this dangerous situation and convert it into this hopefully safer situation. What's going on here is you've got this kid playing with the ball at the side of the road. The driver's in conversation, oblivious to what's going on with the kid there. The risk that you see over time is peaking here above this red threshold, say, and the driver's perceived risk, this blue line, the driver thinks they're safe because they're distracted. They don't know what they don't know. They don't see the risk. They don't feel the risk. They think they're doing a good job. So their perception of risk is low. The actual risk is high. And in the future, there's going to be instrumentation, and this is increasingly the case today, that can scan the environment, know that the driver's on the phone, and alert the driver, so the driver now becomes clueful, as opposed to clueless, about the kid on the side of the road, and then the driver's risk becomes more calibrated. The driver understands when they're on the phone, they just miss the kid, and without the help of the car, they wouldn't have seen the kid. So they become better calibrated as towards the risks that they're taking by being distracted some of the time. So that's sort of a science fiction-y view of the future, but more practically, this is a study that I collaborated with Dan McGeehee at the University of Iowa on, and he's continuing to do really great stuff using a system called DriveCam. And for those of you who have American Families Insurance and teenagers, you can get this system in your car today for free. It's a camera system that has one camera looking forward, as you see here, and then another camera looking back towards the driver and passenger. The camera is triggered by abrupt steering and braking maneuvers. Those snippets of video, 15 seconds before, 15 seconds after, are packaged up and sent home in a video highlight CD to share with the parents, so that the kids and the parents get to go over these video highlights and learn about their driving. So across the top, what you see is a profile of the accelerometer data. So bad stuff happens here, and I'll play this video for you. What happens is kind of difficult to see. This woman, the driver here, she looks down and starts texting. So she kind of does what I did with my music searching, except she's texting, and I'll let you see what's going on here. So she's driving on this rural road. She looks down. You can see she just looked down there. She's looking down. She's looking down. This is a really long time to look away from the road. She bumps the curb. She looks up. Her sister looks over at her, and they smile and think it's all very funny. So if you have children of this age, you may be worried, thinking your kids might be doing this. You should be worried. This happens. It's not that uncommon, and sadly, it kills a lot of people. For all of us, dying in a car is the most likely cause of death. Just about everybody in this room is of that age. So you can see from the looks on these faces that they didn't think this was such a big deal. Did anybody notice the potentially big deal that they almost ran into or could have run into? So there's the school bus. If they had drifted left instead of right, they would have hit the school bus. What was the other thing they might have hit? Telephone pole. So I'll just play it again. You can see that she was on a collision course with the telephone pole that looms on the right. And take a look at the sister as they go towards the telephone pole. So here's the telephone pole coming up here. Doesn't bother her at all. I mean, if you were in the passenger seat, hopefully you'd scream, because she almost died. If the curb hadn't been there, she would have died. And so this is a near-death experience that, because it was, we went and talked to the parents and to her. And before she saw this video, she said, yeah, I know I shouldn't text. I'll be careful in the future, like more careful in her texting while she drives. Then she saw this video and said, oh my God, I'm never going to do this again. So she didn't see what she didn't see, and so didn't feel the risk that she was actually exposed to. So this feedback can be extremely powerful. Among those that tend to get a lot of events, we see a 90% reduction in the frequency of these sorts of events after 6 weeks of feedback. So feedback can be extremely powerful in a domain like driving, where in general we don't crash very often. The feedback is really bad. This can give us very much better feedback to hopefully guide our behavior towards more safe behavior. One of the things that I think is oftentimes common in HCI is the focus on the individual experience, and that's certainly true when we look at driving. There's this focus on the individual driver. I think this quote here says it nicely. You said a bad driver was only safe until she met another bad driver. I think there's a lot of truth to that. It's when two unsafe drivers come next to each other that bad things happen. So a distracted driver can be compensated for by other drivers on the road, but if that distracted driver meets another distracted driver, bad things like this can happen. So what we're looking at is even beyond that, beyond the individual driver interactions, we're looking at the interactions across the social network, drawing some inspiration from this study that looked at the spread of obesity across the social network. So this is using the Framingham Heart Study data that shows that if you have friends that are obese, you're more likely to become obese yourself. Same thing with smoking cessation. If your friends stop smoking, you're more likely to stop smoking. So what we're thinking is that safe driving or distracted driving might also spread across the social network like a disease. And Shannon Roberts has done some really interesting agent-based modeling looking at the spread of distraction across the social network. And she's using that model to guide interventions where we'll be giving feedback to drivers in the context of their social network to change the social norms regarding texting. At least that's the hope, and hopefully lead to safer behavior. So you have this dangerous mix of teens and car keys that causes problems. If we look at the social network, the social influences on driving safety are tremendous. The risk of a crash of a teen is alone higher than an 85-year-old. So if you think you're a good driver when you're 16, look to your 85-year-old great-grandmother and think she's a better driver. That's not what most teens are thinking, but they should be. You put another teen in that car, the risk doubles. Another, the same thing, exponential increase with number of teens in the car. That is part due to the social influence and the distraction of multiple teens in the car. So what we're hoping to do is capitalize on that very strong social influence for the good rather than the evil by providing driver feedback along the lines of what I just showed you, but in the context of the social network so that hopefully we'll be engaging the whole social network in a safer level of driving. So Shannon's going to be filling out that research in the next, hopefully, year. If everything goes well, it should be finished about a year from now. So moving beyond distraction and driver state feedback, one of the other things that's really confronting driving in a big way, could fundamentally change what it means to drive, is autonomous driving. And autonomy, we've probably heard a lot with the drones over Afghanistan, Pakistan. Who's fighting our wars? Who's driving our cars? That may become a lot more indistinct in the near future. And that's driven largely by the incredibly dramatic increase in computerization. And I think we're kind of accustomed to seeing that in the military domain, where you get, with an F-22, about 1.7 million lines of code to control that aircraft. In the newer version, the F-35, the one that's moving towards production now, about 5.7 million lines of code. So these are flying computers. Well, the car is sort of a driving, rolling computer, 20 million lines of code in a modern vehicle's navigation system. So just the navigation system has something like 20 million lines of code. The overall car has something like 120 million lines of code. There's as many lines of code in your high-end vehicle as there are in the Boeing 787. So tremendously computerized vehicles and becoming more so. So one of the issues with this computerization is people's reliance on that technology. So one of the things governing reliance on the technology is people's trust in technology. As computers become more capable, they become, people tend to relate to them as they do other people. So people develop this social relationship with technology, and trust influences that relationship. So a lot of the work that Clef Nass has done, that I'm sure you're familiar with, has shown that people relate to computers as they do other social entities, and trust is one of those constructs that influences that relationship. So this comes down to, oftentimes designers create this cool new technology, but the users don't trust it. And how do the designers engage the users in using the technology the way they hope they would? One solution, and I'm not recommending this, is this idea of liquid trust. This is oxytocin, which is a precursor hormone that leads people to trust each other. So if we gave this audience a dose of oxytocin in the air, you would trust each other in a way that might be surprising. You would be much more willing to engage in socially risky behavior, which is why these manufacturers are suggesting that it's especially designed to boost the dating and relationship area of your life. And so this is a fairly potent chemical that designers might be tempted to use to boost the user acceptance of their technology, but I wouldn't recommend it. One reason is that I think in many cases, technology is already trusted too much. This is a picture of a driver in the north of England who had followed the GPS navigation system's commands, dutifully going from the road to a dirt road to a sort of cattle track, and then eventually couldn't go any further, believing that the GPS system was right, trusting that it knew what it was doing. And what's striking is that this was the view of the driver. You know, you'd think that reality would sort of intercede and make somebody realize that the system didn't know really what they were doing. So they clearly over-trusted the system. Maybe they got a squirt of oxytocin before they went on this drive. I don't know. But this is a challenge. How do you get people to trust technology appropriately? That's just one of the many issues that accompanies the introduction of automation. So as we develop computers to do more and more in the world, we're confronted with a complex array of automation issues that really stem from this basic situation of moving people from active controllers doing tasks to passive monitors watching the computer do the tasks that have been delegated to it. And when you do that, you just don't change, you don't offload tasks and reduce the demands on the person alone. You create new tasks that have to be supported in new ways. And oftentimes that supporting the tasks gets neglected and leads to problems. And I'll just highlight a couple here from some experiences with driving. So one of the general problems is the idea of clumsy automation. Clumsy automation occurs when you take an easy task and you make it easier, and you take a difficult task and inadvertently make it more difficult when you introduce the automation. In driving, that occurs with this really cool system that is supposed to help you stay in your lane. It's a lane assist system that uses cameras to detect the lane lines, and then as you drift out, it'll give you a little beep, and then you know when you're deviating from your lane. So do you need that on a day like today when it's sunny and bright and you can see the lanes? Not so much. So it makes the easy part of driving easier. But then when you need it, like last week when I was in Detroit, I was riding with this guy who had a fancy new Lexus with this system. We got out of the restaurant. It was raining like crazy. It was at night. I thought, this is great. This is just when I need that lane assist system when I can't see the lane lines. And it doesn't work. So just when you need it, it fails. And so that's an example of clumsy automation. Another class of problems with automation, automation-induced errors, new errors that can occur because of the way you now have to interact with it. Specifically, modes. So when you put computers into cars, you introduce modes that might not have existed before. And this is a really striking YouTube. It's not really a video, it's just an audio. And I was going to play it, and I really had second thoughts and thought I wouldn't because it is really disturbing. You may have heard about this. This is the sort of the sentinel event that led to the whole investigation of Toyota's unintended acceleration problem. And this is a 911 call made from a vehicle where the accelerator has stuck on. So the accelerator fully deployed, they're going down the highway in California at 120 miles an hour, and they have no brakes, and they can't turn off the car. And they panic, and it ends badly. So what was happening there is and these were experienced people. The driver was a police officer. So somebody who's kind of calm and collected under pressure can turn on and off a car. This is the way to turn off the car. That was a Lexus. Push button start, not a key that you just rotate. So how would you turn off the car if you're on the highway? It's like you push the button. You know, it's like you push the button to start, you push the button to stop, you get the experience. It's not even as bad as the Microsoft. You have to push start to stop it. It's not really that bad. So you get a lot of practice. You push it, it starts. You push it, it stops. But if you're on the highway, when you're experiencing this unintended acceleration, you push it and it doesn't stop. You push it again, it doesn't stop, because it has a mode that when you're on the highway, you have to push and hold. Like this. So you have to push and hold it for 3 seconds. And when you're on the highway at 120 miles an hour, you're not going to whip out the owner's manual and figure that out. Okay? So this is a case of mode error. You're in a particular mode that you're not aware of. So in terms of HCI, I think we need to think of ways that can systematically identify these complex modes that are going to lead to problems, particularly under points of stress and concern as they felt. And this is some work of Asaf Dagani, who's developed a nice computational approach to describing the state space of the system modes and how these are related to the driver's mental model of what's going on. So you can systematically identify places where the driver or the user in general is going to get confused about the state of the system, so you can design in better feedback so they can become more aware of what's going on, hopefully avoid some of these challenges with mode errors. Here's another interesting mode. If you have the Lexus supercar, which many of you don't, so don't get excited. If you just have a normal Lexus, you can't engage this launch mode. But this is a particularly tricky way to change the setting of your car. And many cars have these sorts of modes buried underneath that are not documented, may not be used. But if I take my Lexus and I engage the launch mode over the weekend just to see how it behaves, and then my wife gets into the car on Monday, all of a sudden that car isn't the car she's used to driving. And that, I think, is going to be increasingly a challenge. Another challenge with vehicle automation is the expectations that people have of the technology, the purpose of the technology, the teleology of the technology, as Peter Hancock has said. This is a good example from Driving Miss Daisy. People at Ford that I've talked to are really concerned that in the near future, when they have a car that can kind of sort of drive itself, people are going to get into that car thinking it's the perfect chauffeur. They can sit back, relax, and not worry about controlling the vehicle. The people at Ford are really worried that the drivers will have that image, that sort of expectation about what the car is going to be able to do. So the designers have one view of the purpose of technology, and that is to enhance the safety. The drivers may have another view, which is to enable texting and watching movies while you drive. The degree to which those conflict, the degree to which the drivers don't understand, don't appreciate what the designers have done, is not really an issue now with the mundane technology into the car, but in the near future, this is going to be a huge challenge to communicate to the driver what the automation is supposed to be doing. So just to conclude, I think HCI has historically and traditionally focused on technology sitting on the desktop. That's quickly changing with the ideas of ubiquitous computing. moving into these complex domains where you have to have computers interacting with the world, where there's high consequences. This is the domain of cognitive engineering. So I'm giving a shameless plug for the book here that I co-edited with Alex Kurlik, that I think does a nice job, as shown by some of the work of Asaf Dagani, in giving HCI people tools for dealing with some of these situations that are going to be confronting us as computers do increasingly exciting and useful things in the world. So with that, I'd be happy to answer any questions.
Questions?
Thank you for your talk. I've noticed, especially in talking with people that aren't really in the technology world, that there's a misconception that the whole point of hands-free technology in the car makes it safer. And there's a growing, I just saw in an ad for Siri integrated to your car. So this is the use of verbal cues rather than physical ones, and people perceiving that as safer. Could you kind of talk about some of those misconceptions about the safety in cars, especially with regards to hands-free technology?
Yes, yeah. The degree to which hands-free technology makes interaction safe is a very controversial topic. So I think there's general agreement that looking away from the road is extraordinarily dangerous. So texting, dialing phone numbers, that sort of thing, very, very dangerous. Talking on a cell phone, there's really mixed results that are out there in terms of how dangerous that is. There's a lot of laboratory studies. Dave Strayer's done some great stuff. We've done some interesting work showing that you can easily demonstrate decrements in driving performance, delays in terms of how quickly you respond to a lead vehicle that's braking. So there's definitely a decrement in performance, but there's also been a whole body of work looking at naturalistic driving, where you instrument people's cars or truck drivers' trucks, and then just watch them drive for a year and record everything that goes on and look at the association between near crashes or crashes and texting or talking on a phone and so on. And what those naturalistic studies have shown is not a decrement in driving performance, but in fact a safety benefit sometimes. And so it's a really difficult set of data to reconcile. So I think the bottom line is that it's complicated. It's the stuff that you're doing when you're talking on the phone that prevents you from going to sleep. So not falling asleep has a safety benefit. When you talk on the phone, you may talk on the phone when you're in low demand areas. So it's almost talking on the phone becomes an indicator of secondary or primary workload demand of the roadway. And so because of all of that, it's really, the jury's still out regarding the risk associated with hands-free interaction. So that's one whole mess there that makes it difficult. The other thing that I think is sort of insidious is the sort of usability paradox, in that you make something safer, each incremental interaction is safer, but because you made it easier to do, now people are doing a whole lot more of it. So instead of having one interaction every once in a while, because it's just hard to get out and text as you're driving, now you're texting all the time because you can do it by voice. So each message, each interaction is much safer, but in total, because it's much easier, you're doing much more of it, net effect might be negative. So how people adapt to this new technology is a huge, huge issue. And I think there is a general finding in psychology, cognitive psychology, that you can't do two things at once without impacting one of them. So when you're talking to Siri, composing a text message, there is a decrement in your awareness for the environment around you, and that decrement can lead to crashes. So it's kind of a longer answer than you expected, but it's a really great question and really complicated. And because of the amount of money at stake with these systems, really, really contentious. So.
Yep. Has there been any research done on
like the amount of information communicated to a driver? Is it better to have like a representation of an analog gauge versus a number, like for speed, an analog speedometer versus a number, maybe versus a word like too fast, too slow,
Yeah.
speed limit, something like that? Is there any research on that?
Yeah, there's a lot of research looking at, in general, analog versus digital displays, and analog seems to be more consistent with many of the sort of tasks that you'd be doing in reference to the speedometer. But when you need the precise speed, having the digital readout can be beneficial. So it depends on the way you're going to use the information, but generally analog is better. And with digital, you have an additional problem of every time you go up or down 1 mile an hour, you get a flicker. And the salience map model that I showed, that flicker will tend to draw your attention down to the speedometer really for no good reason. So, yeah.
Is there a cognitive basis for, analog versus digital, something to do with, identifying information?
Well, depending on how it's presented, it can involve another processing step of translating between the digital information and the set point that you have in mind that you want to maintain. So, yeah, it can be more effortful and more potentially distracting. But relative to scrolling through a list of songs trying to find Springsteen, not nearly so bad. Yeah.
Jeremiah, I enjoyed your talk, and especially the saliency part. We've been struggling with that in the lab right now in terms of websites and making predictions where entry points would be using the saliency model. One of the things that we're struggling with in the graduate students is trying to figure out what type of recommendations do we make once we see that a location is salient, but it isn't co-located with our target information. What do you tell the designers when you're iterating on those designs? Because I saw that you made like a background shading change. What goes into that? Because we know one of the reasons why we use the model is because that information is not consciously available. So we rely on the model to follow the rules, like we're going to process a channel of intensity, orientation, change color, and then the newer motion type of channels. So I was just wondering how you guys have dealt with this more reflective recommendations for the designers.
So at the moment, what we're doing is focusing on developing the model that can predict whatever combination of design features the designer puts up. So the designer creates an interface with font choices, color choices, and so on, puts it through the model, gets a picture like the ones that I showed you, and if that picture is consistent with the tasks the designer wants to support, then it's good. If it's not, we don't really offer specific recommendations in terms of how it should be changed. So we're leaving up to the designer to be creative about trying something else. Yeah.
Yeah, we're really struggling with that right now. We've been going through some iterations, but we haven't got a good process. So I was wondering.
Yeah.
Because we're leaving to the designers as well, and they're struggling. And so we're trying to figure out how to do this more without having to go into like an n number of design cycles. Like how do we just make it the next one's better?
Yeah. So to me, it seems like providing designers with more or less instant feedback about how a design is going to lead to a pattern of maybe long glances that were unintended or long task times, that's infinitely better than what you get out of a usability test a week later. So if you can cut that design cycle from a week to an hour, that's huge. And then the next step of guiding them towards the more optimal design faster, I'd be happy if I can just cut the design cycle by an order.
And that's where we're at. You know, some of the stuff we got impressed, but that next step is. Yeah.
But I think designers are really smart people, and when they get the feedback, they'll very quickly iterate and get an intuition about what features of the display guide behavior in the way they want it to be guided. And so when they get the feedback, they'll be able to act on it better in ways that are more inventive and cleverer than I could ever design. So I'm sort of leaving that up to their genius.
Yes, my question's about infrared technology. We've had spy satellites that use infrared to see through clouds and fogs and all that sort of thing. And recently we've had that helicopter use its full lens to see that bomber in the boat. So why isn't infrared used more in cars? Why don't we put infrared headlights in and cameras so that we don't get these 150 car pileups on the road that we have in California and that sort of because of fog and that kind of thing?
Yeah. So I think that infrared and other technologies are moving into cars. There's an initiative labeled the connected vehicle, which will have active transmitters between vehicles that will relay information from one vehicle directly electronically to another. But this is like RF technology that you can directly communicate between vehicles to give distances, speeds, application of brake, and so on, right through the car, right through the fog, through the whole traffic stream. So your car will know that there's a car a mile ahead that started braking. So that technology is definitely moving in. I think using a broader array of sensors is part of what is going into the advanced vehicles. Whether it's going to include the whole spectrum of technology that sees through fog and sees the lane lines during the day and has the radar to detect the vehicle immediately ahead and so on, that will vary a lot between models. And that's one of the things that I see as being a challenge for the future, is that at the moment you get into a rental car and it does pretty much what your car at home does. Maybe the seat can't adjust in quite the same way, and maybe the windshield wipers on the other side of the stock or whatever. But you have the same sensor suite. 5 years from now, you get a rental car, it may not be equipped in at all the same way as your Mercedes 500S is. And that is going to cause problems, I think. The expectations are going to be there that aren't going to be met as you go from one vehicle to another. Some of them will be able to see through fog, others not. So.
Last question. Oh, I get the last one. Thank you. Great talk. I'm curious, your slide about from the Wired magazine made me remember 15 years ago or so, GM and others had experimented with the heads-up display for the speedometer, et cetera. And it seems to have fallen, maybe it was a marketing failure. But if the issue is to keep the driver engaged on what's outside, I've been caught doing the same thing and I look too long at the whatever. Is there, what went wrong in that approach, and is that going to come back where we'll have this augmented reality experience in a car? Is it the focal distance issue, or was it just what was it?
Yeah, so GM, 20 years ago had a head-up display. Didn't do that well in the market, I think because of costs. So it was fairly expensive and provided very little added value to the customer. It showed the speed. Well, you can look down just a little bit and see the speed. So there wasn't a whole lot of added value that you're paying a fair bit of money for. I think in the future it could change because you can have potentially a large format, sort of like the wired display there, where you can put information that's going to be valuable to the driver. You can put navigation information, you can put warning information, you can put alerts, you can put coupons, you can put ads, you can put Facebook updates. All of that stuff, I think, is poised to go in there. And I think drivers will see value in that. And maybe, almost importantly, the car companies will see value in that. I was talking to a friend of mine who works at Volvo, and he said that if car companies receive 5% of the ad revenue that Google could generate by serving ads in cars, that would change the business model of the automotive manufacturers. They make more money through ads than they would through selling cars. So as soon as you can put ads up in that head-up display, it changes the economics totally in terms of that space. So I think that's why it may be different in the future.
All right. Thank you to John Lee.